goodness. It's waiting for someone to see that. Good. That'll work better. All right, let's come over here and we're going to draw. So we're actually going to get two graphs going forward. And this is going to be kind of the new idea, I think. I think it's really amazing when it works. So here's my first picture. First picture is what you would expect on your horizontal axis. You have y, and on your vertical axis you have y. We don't need a whole lot of values on this. So I have a sneeze. Oh, excuse me. Oh, it's been sniffing these pens. So what was my root? Was it a over b? Is that what it was? A over b? Okay, a over b. So I'm going to put my roots. One of my roots is here. This is a over b. My other root, I'm going to put a big dot. I'll put a dot in a moment. Put a dot down. Can you guys see this pretty blue in the back? Or do you like brighter blue? What?
Draw with it, but I think it's good.
You sure?
Yeah.
All right, well, if it's not, just say try the other blue. Okay, there's that point. There's 1, 0. There's another 0. It's kind of a blackish blue. A bruise. Got in a fight. Oh, and then here's my vertex. We said, which was, what was my vertex? I forgot. A squared over 4b. And the middle point was a over 2b. So notice that that's right smack dab in the middle of those two values. And so I'm going to put my vertex where it belongs, which is right up here. There's my vertex. And I have this parabola that shapes something like that. Drawing two sides of a parabola that look reasonably similar. It's quite a challenge. All right, that'll work. Okay, there's our picture. So that is the picture of f of y. But what's interesting is what it tells us about the solutions to our problem. And that's what I want to look at next. So I'm going to put this next picture right up next to it so we can compare. With this picture, so this is f of y. And now we're going to graph the solution. So this is our solutions. F of y is the right-hand side of y prime.
So it's y prime.
Yeah, it's y prime. I could have just called it y prime, but what I really wanted you to see is that it's a function of y. Now, t and y. Okay, this is a derivative picture here. So you're thinking derivative. What kind of values do I have? I'll grab another color. I'll grab another blue. So when I'm in this region out here, what do I know about my function, my solution? It's decreasing. I know this is increasing, but it's the values of the derivative function that you're interested in. And any value out here is a negative value, so you're going to have a decreasing solution. And that's also the same out here. Wait a minute. So what is all of this between my zeros tell me? I'm going to have an increasing solution in this entire region. I have an increasing solution. What about that? You got a flat spot on the derivative.
Second derivative is 0.
It's what?
Second derivative
The
is 0.
second derivative is 0. What do we call that? An inflection point. It's an inflection point. Where this is an inflection. You have it? Wait, did I just make that up?
And now.
Okay.
Waiting there.
Really? I was already told I couldn't use a book that I wanted to use. And then you say, well, they use different authors use different vocabulary. And I just thought that the vocabulary of calculus has been pretty well established. You gotta be nervous for a moment.
So the inflection point is where the derivative
Yeah, so the inflection point is where the second derivative is 0. And notice that if you take the derivative of the derivative, here the derivative is increasing, so it's concave up. Here the derivative of the derivative is decreasing, so you have concave down.
So if you had a cubic function, it would be where it changes from like that.
Yeah. Yeah, and actually, let's check our mind. Let's find f prime of y. Okay, that's going to be, I can't even see it. I'm thinking of derivative in my head, it's hard. Oh, it's a minus, is it 2by? Is that right? Oh, come on, you can see it somewhere. And if I solve this for y, I have y equals, so I move the a over, so it becomes negative. I divide by negative 2b, that's positive, so I have a over 2b. Ah, and that's exactly what we have. Okay, so far things are matching up. Now, we have these points. We have my big dots, my dot at 0 and my dot at a over b. And what is unique about those two dots? It's the derivative is 0. So when the derivative is 0, what do you know about the solution there? It's flat. Yeah, it's the derivative of that function at that value is flat. But wait a minute, this is the graph of y. It means it's always flat. So this is just y equals a constant. Well, that's just a graph that goes out forever. So here's what I have. I have a point here at what was it, a over b. And my point down here at 0. And what I have is, all I know about those is that any value of my function, when y is a over b, my solution is going to be 0. So these are my steady states. So when I get close to those, it's going to approach that. Yes?
So is the inflection point, because I wasn't super familiar with that term either, but so those are also basically inflection points of y.
Yes, yeah, of y, correct, correct. Yeah, right, because you have to remember, we're working with y prime and y prime prime. So let's take a look at our solution. If we're between 0 and a over b, what do we know about our solution? Let's start with the easy one. What do we know about it? It's increasing, right? It's increasing. And also, when it gets to the height of a over 2b, what do we know happens? It changes concavity. So when I'm at this value here, I'm going to put it, it's probably going to get drawn on, a over 2b. What I would have is I have a solution that's coming up to a over 2b. It's concave up. When it hits a height of a over 2b, it becomes concave down. But it's still increasing. Now, can it cross a over b? No, because then you have a derivative that has two values at the same place, and a derivative doesn't do that. It's a function, so it's still increasing, but it just gets really close. You could start it out further over here. You could say, maybe my function starts like this, concave up. It's a over b. It's going to start going concave down. Now here's a question that some books spend a lot of time on, and this author doesn't. Will these solutions ever cross? Why? They're shifts. That's exactly right. And what else would have to have? If these crossed, what would that imply? Well, it would imply that they have different derivatives at the same value. But the derivative is already our value that we have over here. It's just f of y. So these can't ever cross, but man, can they get as close as you want. And you can have functions that come up, solutions here, and you can just fill the page with these. But they won't ever cross. Now, let's take a look. What happens if we're above a over b? For example, say we're up here. I'm going to call that maybe we start there, or some y of 0. What do I know about my function if I'm above a over b? I'm somewhere up here. We know that it's decreasing. Okay, so now I have a function that's coming down. But wait a minute. Can it cross? Can't cross a over b. As it approaches a over b, it's approaching a slope of 0, and so. And you can start y of 0 higher. What if my function started below 0? What do I know about it? Well, what do we know? It can't cross 0, that's correct. So is it going up towards 0, or is it going away from 0? It's going away because it's a decreasing solution. It's a decreasing solution, and you have something like this. Here you are. That was perfectly clear.
How is it a decreasing solution?
Because the derivative is negative. These are negative values out here. So your slope is going to be down. So you go down. Any other questions on that?